I think so. The Thurstons well, the uniformization or geometrization or hyperbolization or whatever, the Thurstons work on this topic should be very famous. And well, actually, now because of the Perelman's work, and now it has become more famous. And actually, I heard from Sadayoshi Kojima that there will be some fashion show on Thurston geometrization in Japan, and a fashion show by Issei Miyake, who is a very famous designer. So now it's very popular. But what I'd like to introduce today is not the Perelman's work, but Thurston's original uniformization theorem for Hakel manifolds. So so let me start with the basic notions in a three-dimensional topology. So what we are interested in is a compact three-manifold M. And well, there is a basic theorem by Kunazer and Milner, which says that any compact three-manifold can be decomposed into prime. So the prime manifold. So there is a prime decomposition of the compact three-manifold. So and that is unique. So the prime decomposition is just the connected sum. So any three-manifold can be decomposed into finitely many prime manifold. So the three-manifold is said to be prime if it doesn't admit the prime decomposition anymore. So if it cannot be decomposed into non-trivial connected sum, then it's called prime. Okay. And prime manifold. So there are two kinds of prime manifold actually. So one is something called irreducible manifold, and the other is just well, we assume all manifolds are orientable here. So the other is just the product of the circle and S2 circle and sphere. Okay. So three-manifold is said to be reducible when every sphere, two sphere in M bounds a ball in M. So it means that if there's no essential embedded to sphere, then the manifold is said to be irreducible. Okay. So because this prime decomposition is unique, this is unique. Actually, the existence of the prime decomposition is proved by Kunazer, and the uniqueness is proved by Milner. Okay. So, because this decomposition is unique, and to consider well the oldest compact three-manifold, it would be sufficient to consider only the prime ones. And because the prime manifold is either irreducible S1 times S2, then and we know well about S1 times S2, so that it will be sufficient to consider reducible ones. Okay. So now, from now on, we only consider irreducible manifold. So we only consider right? So, so we may allow the M to have a boundary in general, but we assume they're compact. Okay. Now, so there's now. So now we reduce the general theory to the theory of reducible three manifold, but still it's too general. So we'd like to introduce some technique to decompose manifold further, so that we get more simple ones. So that's called the theory of Jacob, Schering, and Johansson. So the JS, what it's called, the JSJ theory is in general the decomposition along the tori and the annuli, but in this in our settings, the decomposition along annuli doesn't concern us. So we only consider the torus decomposition. So a torus. So we consider a torus embedded in a free manifold M, and in general, if there is an embedding of some surface into M, we assume all the things are orientable. So this is orientable, and this is orientable. Then this is called incompressible if the pi1 of S injects into pi1 of M by the homomorphism induced by the inclusion. So if this is injective, if this is injective, then it's called incompressible. Actually, this is a kind of the special case of the incompressibility. Actually, there is a more general definition, and if you assume that both of them are orientable, then this definition is equivalent to the original definition of incompressibility. Okay, so torus decomposition is a decomposition of three manifold along incompressible tori. So we consider incompressible torus here. So so Jacob, Schering, Johansson theory implies that any irreducible three manifold can be decomposed into two types of three manifold. One is Seifert fiber manifold. And the other is something called toroidal manifold. So, three manifold is, three manifold M is toroidal if any incompressible torus in M is parallel to a boundary component. So Seifert fibered manifold is something, it's a kind of the generalization of the S1 bundle over surface. So this is the S1 bundle actually over two orbifolds. So, so generically, there is a fiber, S1 fiber, but there is some singularity. So above the singularity of the two orbifolds, the fiber is also circle, but this circle is, so in the neighborhood of the circle, there is no product structure, but there's something like, so in a singularity, there's fiber like that, and all the fibers near this one wraps around the fiber finitely many times. So if you have a solid torus and we regard the core of the solid torus as the exceptional fiber, then all the ordinary fibers goes around like PQ curve on a torus. That's what the singular fiber of the Seifert fiber manifold is. Okay. So any S1 bundle over closed surface or S1 bundle over compact surface is also a Seifert fiber manifold. That's the special case when there's no singular fibers. Okay. So this kind of manifold were well understood before the theorem of Thurstons. So what is not well understood is this one. So the toroidal three manifold. Okay. So what Thurstons proved, what geometrization theorem in general says is any toroidal manifold. Actually, there's a toroidal Seifert fiber manifold. Some example of the Seifert fiber manifold which are toroidal. Except for that, the geometrization conjecture says that any toroidal non-Seifert fiber manifold are hyperbolic. Okay. So geometrization conjecture now it's theorem, Perelman's theorem says that any non-Seifert toroidal compact. Actually, because we allowed, okay. And I will explain more about how we regard the boundary, which is not torus. But anyway, so the geometrization conjecture said any non-Seifert toroidal compact three manifold admit hyperbolic structure. Okay. And now this is known to be true, thanks to Perlman. But so the Thurston himself proved this. A special case is Thurston uniformization. What is called the uniformization is a special case of this geometrization conjecture, and the assumption that M is Haken. So I haven't defined yet what this term, what Haken manifold. So a compact free manifold M. So we always assume that manifold is compact. So compact free manifold M is Haken if M is irreducible and there exists some surface embedded in M which is incompressible. Well, so because this is reducible, I mean, well, in the definition of incompressibility, I didn't say that the surface should be assumed not to be a sphere, but so. When we say something incompressible, we already assume that is not sphere. Well, okay. So this should be some surface which is not sphere, so that it might be torus or genus 2 or genus 3 or whatever. But anyway, so this S has infinite fundamental group, okay? Because it's not sphere, we assume that it's orientable, okay? When M has a boundary, it might be the annulus. Okay, so it might be disk. Well, okay, so that in that case, the fundamental group is not infinite. But anyway, okay, so we suppose that M is closed, for instance, or S is closed, for instance. Then S has infinite fundamental groups, and because it is incompressible, that its fundamental group injects into that of the M. Okay. So the fundamental group for M also must be infinite. Well, this is true even when S is a disk, actually. Okay. Well, so I haven't defined what the incompressible disk means, but anyway, so it's not. So it might be better to consider only the non-disk, non-sphere case. Okay. Anyway, so the Haken manifold has infinite fundamental group, and so for instance, the 3 sphere is not Haken, or length space is not Haken, but also there's some non-Haken 3 manifold. You can construct the Seifert fibered manifold, which is not Haken, and also we know there is no Haken hyperbolic free manifold. So, the condition that the M is Hagen is a kind of restriction, but this is, well, a kind of generic situation. And if manifold is Hagen, then there is a technique of hierarchy. The technique using hierarchy to make the induction work. So there is some notion of hierarchy, and that makes induction work. So what is hierarchy? So if you have a Hagen manifold M, then by definition there is some incompressible surface S embedded in M. Then we can cut M along S. So well, if you have M like this, and inside M there's surface S like that, then we cut. So what you get might be connected or disconnected. But anyway, you get some new compact 3 manifold by this operation. And, well, it is easy to see that if M is irreducible, then the manifold obtained by cutting along S is also irreducible. Now, actually, if a manifold, irreducible manifold, has a boundary, and is not, well, and the boundary, if the boundary is not a sphere, then we can show that it is Hagen. So the manifold obtained by this operation is also Hagen. Well, if it's not actually in the last step of this this operation, then you get the 3 ball, which is not Hagen. But before reaching the final stage, you get the Hagen manifold. So you can continue the process, and finally you get the 3 ball or union of finitely many 3 ball. Well, you can choose if you choose appropriate incompressible surface, you can make, well, I'm not sure. No. So it might be disconnected union of the 3 ball. So this is the process of the hierarchy, the process of the cutting along the incompressible surface. So this kind of the construction is called the hierarchy. So if you would like to prove something for general Hagen manifolds, then what you can do is to use the induction. So if you can prove something, well, at the last stage, and if you can show that this condition is preserved along this operation, under this operation, then you can show that the something is true for general Hagen manifold. So the existence of this hierarchy guarantees that the induction works. So An example of such an argument is the Walthausen's theorem, showing that if suppose that there are two, maybe it's better to assume they're closed Haken manifold, and if there is a homotopy equivalence, then F can be realized by, so F can be homotoped to a homeomorphism. So any homotopically, or any homotopy equivalent Haken manifold, closed Haken manifolds are homeomorphic. Or there's another theorem about Hausen. Number two, that if they are, well, they're under the same assumption that if there are two, it might be, well, so this doesn't concern us. So just I just state one of them. Okay, the Walthausen theorem says that the homotopy equivalent three manifolds are homeomorphic. Well, homotopy equivalent closed Haken manifolds are homeomorphic. So his proof of the theorem relies on the existence of a hierarchy. Actually, Walthausen didn't call such manifolds Haken, and in his paper the Haken manifolds are called sufficiently large reducible three manifolds. So if you look for the Walthausen's paper, then the title doesn't contain the Haken. It says the sufficiently large, something sufficiently large three manifold. Okay. Right. So the Thurstons theorem, the Thurstons uniformization theorem for Haken manifolds, also uses this kind of technique. The existence of the hierarchy is essential in his proof. So maybe so it's okay. So because I have plenty of time, so before showing how to prove that, let me just give you an example of the hyperbolic metric, and also I'd like to explain what we are considering in the case of the manifold with boundary. Okay, so one of the most famous example of the hyperbolic three manifold is, well, I'm not sure this. Okay, this the upper, lower, and is this the right way to draw a figure 8 knot? This should be figure 8 knot. If it is not correct, then just please ignore some mistakes. And so this should be the figure 8 knot. Okay, so that complement. So this is a knot embedded in the three sphere, and the complement of the figure 8 knot is known to be hyperbolic. So there is a hyperbolic metric on S3 minus figure 8 knot. Figure 8 knot. Okay. This is figure 8. Okay. And so because the complement of this figure 8 node is not compact, so it might be, well, so instead of considering the complement itself, sometimes it is more convenient to consider the complement of the tubular neighborhood of figure 8 node. So then you get some manifold with torus boundary. Okay, that is compact. And when we say that there is a hyperbolic metric, then we are considering the interior of this manifold, which is the same as the complement of the figure 8 node. And this part, the boundary, near the boundary, the metric is, the hyperbolic metric is Z times Z cut, which I explained yesterday. So it's a quotient of the hollow ball by two independent parabolic elements. Well, the group is generated by two independent parabolic elements. Okay. So, okay, this is one of the examples of the hyperbolic free manifold. Okay. So if you have a torus boundary, then the hyperbolic structure there is just has the structure of the cusp. So, and when we consider a manifold with boundary having higher genus, then so something like this. So so if M has a boundary component which is genus 3 in this case, then when we say M has a hyperbolic structure, that means there is some geometrically finite, well, Kleinian group G, which I explained yesterday, such that the convex core of H3 over G is homeomorphic to that. So when you have a higher genus boundary, then what you consider the geometrically finite Kleinian groups and its corresponding hyperbolic free manifold. Okay. Okay, so that's what I mean by the hyperbolic structure on the Hagen manifold. So what uniformization theorem of Thurston claims is that any hyperbolic free manifold, any Hagen free manifold has a hyperbolic structure in this sense. So that if you have a boundary, then the near torus boundary, the structure is a cusp, and if you have a boundary of higher genus, then that means it's realized as a boundary of the convex core of some geometrically finite Kleinian group. Okay, is it clear? Okay. Any questions so far? So yesterday there was no question from the students, so I'd like to have some questions from the graduate student. Is there any questions? No, okay, everything clear? Yes. So if you, yeah, so this boundary components correspond to a domain of a component of the quotient of the domain of discontinuity by G. Yes, exactly. Yeah. Any other questions? Okay. Right. Okay. So now, let me show how to prove, well, Thurstons uniformization theorem. Well, it's very complicated proof, and actually, the Thurston himself planned to publish his proof of uniformization theorem by writing a paper consisting of 7 parts. And the first part appeared in Annals of Mathematics. And we have the preprints of the second part and the third part. And you can download it from the website. But the fourth part, fifth part, sixth part, and seventh part, they don't exist at all. So you cannot find them anywhere. But actually, there are some books containing the proof of the Thurstons uniformization theorem. But for instance, Kapovich's book on what the title, the discrete groups. Do you remember the title of this Kapovich book? And the Kapovich book published from the Berghäuser that contains the proof. But the proof is different from the original proof of the system. And there's also the book by Otar containing some part of the Thurston proof. But if you would like to know the original proof of the Thurston, then the best reference is Morgan's article on which is contained in the book whose title is the Smith conjecture. So it contains the chapter written by Morgan, whose title is Uniformization of the three manifold or something, not by Thurston. Okay, that shows the outline of the Thurston's original argument. Okay. So you can well see the reference in my lecture notes. So okay. Now, so what I'd like to show today is the first step of the proof. First step or last step. This should be the last step because the induction begins from there. So that this should be the last step. So what I'd like to show is the last step. But let me say something about the first step first, and after that I turn to the last step. The first step is, so in the first step you have a ball, and so ball is hyperbolic, well, in a sense, it's a Poincare discrete of hyperbolic. But if you consider such a hyperbolic structure, it doesn't. It's not useful for this construction. But what you would like to have in the last stage is some hyperbolic polygon, hyperbolic polygon, no, polyhedra. Okay. Polyhedron or polyhedra, or there might be several polyhedra. And the existence of some special structure of the hyperbolic polyhedron is guaranteed to exist by Andreev's theorem. So Andreev's theorem says something like this. So let me see my note. Okay. So if you have a triangulation, so you have a sphere, and the triangulation of a sphere, P is a triangulation of a sphere. And suppose that for each edge, well, we assume that this is not the tetrahedron. And for each edge of T tau, so this is the set of edges, we assign an angle. So theta E is an angle. It lies between 0 and half of the pi. Okay, and assume that for any cycle in so this is just a cycle. This might not bound a face, so there might be something like this inside there. If the sum of the theta I is greater than or equal to pi, then this bounds a face. This is a condition. So the tau. And for the boundary of the face in general, so conversely, if the boundary of for any face, its boundary has a value whose sum is greater than pi. Okay. And moreover, we assume that if there is a cycle by 4 edges, and if the union is 2 pi, well, this happens only because these angles must be less than or equal to half of pi. Then if the sum is equal to pi, then that means that everything is equal to the half of pi. Then, well, this bounds a union of 2 faces. So there's something like that. So this is face. So these two are assumptions. Then the Andreev's theorem says that then there exists a hyperbolic polyhedron. So whose faces are dual to tau. So there's a dual cell decomposition of the sphere. So something like this. And so each face of the dual cell decomposition corresponds to a face of a hyperbolic polyhedron. Well, I sorry. So hyperbolic polyhedron whose face is dual to tau, and the dihedral angle between 2 faces corresponding to. So if the two faces are adjacent, then there should be some edge corresponding to the shared edge. So each edge of tau corresponds to some two adjacent faces. Okay. The two correspond the dihedral angle between the two faces corresponding to E is equal to theta of E. So this data, this angle data theta, is realized as a dihedral angle of the hyperbolic polyhedron. That's what Andre's theorem says. And this is the first step of the uniformization theorem. So starting there, so the induction work start work, and you reach the final step here. So in the final step, let me assume that M is M is well, in general, we have to show that the existence of the geometrically finite structure. But, let me restrict ourselves to the case when M is to the, closed. Well, if you have a torus boundary, it's okay, but, suppose it's closed. Then, what you get is the last step is the situation where the M has some incompressible surface, closed incompressible surface, and you cut M into 2 or 1 if S is, this might be possible, that if the surface S is non-separating, then what you get is something like that. So either this is okay, but anyway, so at the last step, what you have to show is you have two Haken manifolds with a higher genus boundary, and both of them are assumed to have a geometrically finite structure, and what you get is the closed hyperbolic 3 manifold. So you'd like to show that there exists a closed hyperbolic structure on M, which is obtained by pasting two geometrically finite hyperbolic structure. Okay, that's what you have to show in the last step. Okay. Actually, there are two different situations. The first is the case when, there are two cases. There's the non-fiber case and the fiber case. This is the last step, the final step of the induction. Non-fiber, so what I mean by fiber case, that is the case when M is surface bundle over this one. If you have a S bundle over S1, this surface, this fiber surface S is incompressible. So if you cut it along a fiber, then what you get is just the product of the S and the unit interval. Okay, right? So this case is a kind of special. So the technique which would be used here doesn't work for this case. So this should be treated separately. And actually, in the series of Thurstons paper on the uniformization theorem, the part 2 deals with this case. Okay, and the non-fiber case is more generic case, and what you get is not such a manifold, but well, something like that. So so for non-fiber case, you get two Haken manifold with boundary, or this might be connected, but still this is not homomorphic to the S times I. So this is more complicated free manifold. So this boundary component is not homotopic to the other component. Okay, that's the situation. Okay. So the proof of the fiber case is well related to a theory of Kleinian groups, which is called the double limit theorem. So this is to prove this you need double limit theorem. So I think Inka will talk about double limit theorem. Okay. And the other case, the generic case, is we need to use what is called masked combination theorem for this generic case. Okay. So, well, by the way, so I said that there is a hyperbolic structure on the figure knot complement. Okay, that's fiber case actually. The figure knot complement is one punctual torus bundle over S form. So if you try to use this kind of argument for figure knot, then it goes this way. Okay, and you need to use the double limit theorem. Well, to show that figure knot complement has a hyperbolic structure. If you try to adapt this argument. Okay. So actually, it's much easier to show that figure knot complement has a hyperbolic structure. It can be decomposed into the union of the two tetrahedra, and each tetrahedra can be realized as a hyperbolic one. And pasting them by isometry, you can get hyperbolic structure on the figure knot complement. But if you like to show it in this framework, then what you have to do is this double limit theorem. Okay, then so for the rest of the time, I'd like to show how this generic case can be dealt with. So I said that it relies on the masked combination theorem. So what is masked combination theorem? So it's kind of the so suppose, well, okay, let me state it. So suppose you have two. So consider that situation. Then M is so M has some incompressible surface. Well, this is a special case of Masket. Masket theorem is a very general one, and this is just a special case of Masket combination theorem. So if you have incompressible surface in M, and you get M1 and M2, well, which might be, so, okay, so well, suppose S is separating first. Then you get M and M2, two manifolds by cutting M along S. And suppose there is well, geometrically finite. Well, we assume this has genus is greater than 2, greater than or equal to 2. And so suppose there is geometrically finite Kleinian groups. G1 such that the convex core of G1, H3 over G1 is homomorphic to M1, and G2 such that the convex core is homomorphic to M2. Okay. Right. So the situation is like this. So you have surface S in the M1 and M2. So pasting M1 and M2 along S, you get M. Okay. And M1 is homomorphic to the convex core of some geometrically finite Kleinian groups. And this is also homomorphic to a convex core. Okay. And further, we assume that so if you, because this is a Kleinian group, if you take a subgroup of G1 associated to the, well, this is because this is incompressible surface, pi 1 of S inject into pi 1 of M1. So there is a subgroup of G1 corresponding to this fundamental group. So exists G1 S inside G1 corresponding to pi 1 of S. Also, you have some group G2S inside G2 corresponding to pi 1 of S. So. And suppose these two groups are conjugate each other. Then you can, well, construct a Kleinian group which is an amalgamated free product of G1 and G2 along G1 of S. So G1 of S is identified to G2 of S, and then you can take an amalgamated free product, and is realized as a Kleinian group. Actually, so as we assume these two are geometrically finite, this is also geometrically finite. that is the masked combination theorem. And furthermore, the convex core of this manifold is homeomorphic to M. M is the original. So that you can place these two structures along the surface if the restriction of the Kleinian groups to the surface is the same as the one obtained here. So that so you have two Kleinian groups corresponding to the pyronovers. One lies here and the other lies there. So if these two are conjugate each other, then you can paste them along this one and get a larger Kleinian group. That's what masked combination theorem says. Well, the same kind of theorem holds even when S is non-separating.